Hello everyone, my name is Harrie Oosterhuis. I'm very happy to talk to you through this recording. And for this keynote, I would like to present a paper that we published when I was a visiting research scholar at Google Research, which we sent and presented at KDD 2024 last year. The title of this work is Reliable Confidence Intervals for Information Retrieval Evaluation Using Generative AI. I would like to thank my co-authors Rolf, Jagerman, Zhen, Xuanhui, Wang, and Michael Bendersky. The problem setting of this work is around evaluation metrics for rankings. So these are very common in information retrieval and also very common in recommendation. So very simply put, we want a metric that tells us how good is a ranking, and we can aggregate that to say how good is a ranking system. The particular metrics I'm going to talk about are all kind of precision-based metrics like precision at 5 or DCG at 5. In the example that you see on screen, we have 5 documents. 3 of them are relevant. 2 of them are not relevant to the specific ranking context or query. I'm going to use the word query in this presentation. So if we compute precision at 5, we end up at 0.6. If we compute DCG, it's going to be about 1.93. Now, these values are very important if you want to compare systems, or if you want to do some form of research and development. You really need to rely on metrics like this to know if you're doing well. The existing way, or the most reliable way of doing this, is through human evaluation. So if you have a human expert that tells you what items are relevant or what and which ones aren't, you can use those labels to then compute these metrics. You might also use specific explicit user feedback or something like this. But usually this is very expensive, especially if you need to get experts. It's very expensive to get a lot of those because you need to pay for someone's time. It takes a while to get them. It costs a lot of money. So with the recent advances that we've seen in generative AI, and particularly with large language models, a very sort of obvious alternative to human evaluation is using LLM generated labels. So I can use my large language model, I can ask it, is this document relevant or not? And I can that way get a set of labels, and then I can use those labels for my evaluation and maybe even my optimization. So in this case, I've asked the LLM also to give me relevance labels. And then I can use them to compute precision and DCG, which are then according to these generated labels. Of course, this is really cheap, because I only have to pay for my compute time, which is usually much cheaper than human time. The problem, however, is that it's not quite accurate. So there's going to be a disagreement between my human expert and my large language model, or between maybe the users that I have in my large language model. Either way, as you can see in this example, I am likely to misestimate these metrics, right? So in this case, I'm underestimating the performance of this ranking in both metrics. So we have basically gained a lot of, we saved a lot of costs, but now we are in an unreliable setting, right? So if we go all in on LLM generated labels, we don't have reliable conclusions. The question that we had for this paper was, is that even a possibility? Can we use LLM generated labels to do some form of evaluation for rankings, but draw reliable conclusions? And what I'm going to work towards in this presentation is an approach where instead of just getting a point-wise estimate, we're going to estimate a confidence interval. And this confidence interval, so let's say with 95% confidence, can tell us where the user or the actual value that we care about would be in. So in this example, we can see from the confidence interval that there's quite a lot of unreliability in this LLM generated evaluation metric. The main contribution is thus. We have 2 methodologies that we propose that build reliable confidence intervals around these information retrieval or ranking metrics. The key part is we're going to use many LLM generated labels, so large numbers of LLM generated labels, but a few ground truth labels. We need a few ground truth labels to ground our reliability somewhere, but we can still use the sort of large availability of large language model generated labels. The first method is a quite straightforward application of prediction-powered inference. Prediction-powered inference is an existing method. Please check out the paper in the that you see here cited at the bottom of the slide. This is from 2023, so about 2 years ago. And the main idea here is we're going to use our large N LLM predictions. So large N means we have many LLM predictions, and small N ground truth labels. So we have a few ground truth labels, but many LLM predictions. Now, the thing that we can do here is because we can get our LLM predictions anywhere. We can have them on the same data points as we have the ground truth label. So for those data points, we have both the predicted label and the ground truth label. So now we can make a new mean estimate. You might say, well, why don't we just average the ground truth labels to get an estimate of our mean performance? Well, you'll see. So our new mean estimate here is going to be our prediction-powered inference, so PPI estimate. It's over a set of queries. So I have a data set of queries for which I want to know the mean performance. So let's say the mean precision, and this is going to help us there. The mean prediction is where we start. So we start with what is, if I take the LLM generated labels, what is my mean prediction? So this is the metric value for one query, and then I have them for n queries. So this is my mean prediction. So as you recall, this is likely going to be incorrect. It's going to be some form of bias here. So the second part is going to subtract that bias. And we do that by estimating it from the data points where we have both a prediction and a ground truth observation. So I can look at the difference between those two. And then, of course, I have n observations. So the average difference is basically subtracted here. This means my estimator is going to be unbiased. Right? So we start with the biased estimate of the predicted labels, and then we subtract the difference that we observe, and that's going to be debias in expectation. So we have an unbiased estimate. This looks very complicated. It's much more complicated than averaging the ground truth labels. But the reason we do this is because it has going to have a different variance than if we just use the ground truth labels. Now, if we construct a standard 95% confidence interval, assuming this is normally distributed, we end up with the following, right? We end up with our mean estimates of PPI, and then we either plus minus, depending whether we look at the high value or the low value, 1.96. This is pretty standard if you want 95% confidence. The square root of the variance of the error divided by the number of observations of the ground truth, plus the variance of the predictions divided by the number of predictions that we have. So the variance of the error is the variance of this part on the right here. The variance of the prediction is the variance of this part of the estimator here on the left. Now, what you can see is that if we now get more predictions, if we get more labels, my confidence interval is going to shrink, which is nice. That means I can use my large language model generated labels to get better confidence intervals. At the same time, it's not going to go to 0 unless the error is also small. So that basically means, okay, more labels is better, but we can't bootstrap our way out of garbage predictions, right? If the predictions are pure noise, this part will not be removed, so we will still have, we will not go towards a 0 confidence interval. So this is a very straightforward way to do it. It's very neat. I really recommend anyone use prediction-powered inference if they're dealing with machine-generated labels in combination with ground truth labels. The downside here is that we can only do this on the dataset level. So only on an entire dataset can I now get a confidence interval. But I would also like to get a confidence interval on the query level. I would like to say for a specific ranking, how good is this ranking or not? And that's not something prediction-powered inference can do for us. Nevertheless, I really like the simplicity here, and I would really recommend this method. Okay, for that other setting, so if we want also query level confidence intervals, we looked at conformal risk control. So again, this is an existing framework, so not a method, I would say, but a framework which you can fill in to derive a method. Again, I really recommend the paper that has similar authors in the prediction-powered inference paper. See the citation below here. Again, we have many large N LLM predictions, small N ground truth labels. What we're now going to do is we're going to sort of perturb our predictions to be either more optimistic or more pessimistic to make our confidence interval. And the way I'm going to do that is by looking at the relevance prediction distribution. So we use an LLM in scoring mode, so it can give us a prediction distribution. So for each token that it can output, we can look at the probability. It gives us a distribution. So here are 3 documents. For this document, it's pretty certain it's irrelevant. This one, it's uniform distribution. And here it is pretty certain that it is quite relevant. Now, if I want to be more optimistic or pessimistic about these documents while still following sort of the predicted distribution, I'm just going to remove probability mass either from the front or the back of these distributions and then renormalize. And you can see here, so 0 if I leave it unperturbed, 1 means that I'm extremely positive, and -1 means I'm extremely negative. You can see by the way these curves move that it's easy to be very optimistic about documents where we already think they're relevant, and it's pretty difficult to be pessimistic about them, and vice versa. It's really easy to be pessimistic about documents that we already think are irrelevant, and difficult to be optimistic about. With these optimistic and pessimistic predictions, I can very easily create an interval on the query or the dataset level. I can just use these for all of the documents, compute my precision or DCG, and I get a high value or low value, and that gives me an interval, right? The important part here is that we know that this interval can become a valid confidence interval if we calibrate it well. So if I take my interval, I know that it can be, if I take the maximum values, if I take 1 and -1, it's going to be the entire possible space of values. I know that the real interval that I want is somewhere in between. So I know that I can find values which will be a valid confidence interval. All right, so we know that this should work. The real question is, where should this parameter be, right? How optimistic and pessimistic should I be such that I can guarantee a 95% confidence interval? And this is precisely the kind of problem where conformal risk control is really good at. So we can use that framework here to find our method. There is a difference. So conformal risk control is really about a single parameter. We have 2 parameters. Luckily, we can make this a sort of recursive problem. We can make it 2 problems where I first calibrate one of sides, so let's say the high end of the confidence interval, and then based on where I place that, I can then place the one at the low end. Through this property that we have here on screen, I know that that's going to be the correct confidence interval. To do this, we need a loss function. The loss function is going to be very simple. We need some examples like a calibration data set, and then on that calibration data set, we can see how many times, for instance, the high end of the confidence interval is above the real value, or how often the low value is below the true value that we have. And this allows us to optimize, right? So the loss is basically the coverage. Then through binary search, I can find the confidence interval that matches the confidence value that I need. So if I need a 95% confidence interval, I'm actually going to look for a confidence interval that's above that. That's, I don't know, 97 or something. But it depends on how much data we have in that calibration set. So if we have very little data, I need to correct for that. There's a known correction for that. It's on screen right now. This is very standard. I really recommend this paper as well if you want to know the details of how this works. But basically what I want you to understand is I can use binary search to search through how optimistic or pessimistic we should be. I mentioned that we need a calibration data set, right? Because in order to sort of find these values. For the data set, we only have one data set, so I don't have other examples, but I can do subsampling or bootstrapping to create many smaller data sets on which we can then do the calibration. And again, we do binary search, right? So I go over all of these subsets that I have, and I look. So if I want 95% coverage, I look for a bit more than 95% coverage. We can guarantee, if that's the case, that if you were to continue this process, if you were to continue subsampling or bootstrapping for those new samples with the coverage that we have, so with a 95% chance, the actual value on those samples is going to be in my confidence interval. And if these samples are representative of the whole data set, then we know that it's also going to be 95% in there. So that's how this works. That's a very short version. Just to give you an idea, because I explained quite a lot, I'll walk through the whole method once more. This is quite complicated. I'm supposed to prediction-powered inference. But we sample a set of queries from the ground truth data. If I want individual queries, by the way, if I want confidence interval on individual queries, these can be individual queries. This can also be batches of queries if I wanted on sort of an average. I calibrate the optimism and pessimism parameters on the n ground truth labels. So on that ground truth data, I can calibrate my parameters. Then I can use all of my data, so even the data where I don't have a ground truth, to again compute these low and high estimates with these calibrated parameters, but now on the entire data set. And then on the entire data set, I can create a data set level confidence interval. For query level, you don't need to aggregate. You can just use the query level confidence intervals. Let me show you sort of the experience that we did to evaluate our setup. We used the FLAN UL2 in scoring mode. So the scoring mode allows us to look at the token distribution, so we get label distributions. On the TrackDL and Robust4 datasets, these are very standard datasets. We did not do prompt engineering. We gave the same prompts or the same instructions as we would give to human labelers. This is just to improve reproducibility because there are many things you can do with prompt engineering that we did not want to go into. I want to start by looking at sort of the performance that we saw. So what we actually did is we split the data into 50-50 calibration and test set. And then we're going to vary the size of the calibration set to look at the effect of data efficiency. But I first wanted to quickly look at DCG at 10 of these different rankers that we have. So we have a random ranker, BM25, the LLM itself, used both for ranking and evaluation, and a perfect ranker if you would follow the human labels. And you can see the LLM is quite good at getting correlations right, but it overestimates its own performance. It thinks that the LLM ranking is the best. It also, the absolute values aren't quite correct, right? So even though like the general correlations are right, it isn't quite right. So it's making errors. What we're going to do is we're going to make 95% confidence intervals around BM25. And I compare prediction-powered inference and conformal risk control with classical bootstrapping. So that's our main baseline. And all the results that you see are averages over 500 repetitions. What you see here on the x-axis of these graphs is the number of human-labeled queries that we use. So this is the amount of ground truth data that we have. And then the width and coverage of our confidence intervals. What we see is that both of these methods improve in coverage. They give about the same coverage or width, but they improve on one of those aspects. But which one varies per data set and also per method. So over here, we see that PPI gives much better coverage, but its width is about the same as bootstrapping, whereas CRC improves the width, but it has only slightly better coverage. And what's especially important on both of these data sets, we see that you need fewer ground truth data points to get the same coverage as bootstrapping. Especially here on Robust, we need fewer than 40 labels, whereas the bootstrapping needs at least 100. We also checked out query level performance, right? So what you see here, each blue dot is a predicted query performance. The green and the red dots are the actual performance. And then they're red if they're not inside of the confidence intervals, which are the blue bars. We can see that we easily get 95% coverage. We also see that the width varies per query. So it's not that we have the same width everywhere. And on average, we can be more confident about low performance for some reason. We simulated a setting where we made the predictions adversarially worse or with an oracle sort of better by interpolating between very incorrect, the worst predictions and the best predictions. And the coverage remains the same, but the width responds how you would expect them to. So the widths get bigger if we make the labels worse. They get better if we make the labels better. This is what that looks on query level. So here we interpolate with an oracle, so the labels get better. You can see here on the right that the intervals are smaller. If I now increase this interpolation, they become even smaller. And you can see that even for some outliers like this point over here, that it still understands that it's an outlier. It's not that all the widths become smaller. It does sort of capture that variability quite well. What this means is that if we ever get better predictions, we likely also get better confidence intervals. All right, for the sake of time, I'll conclude. We can construct reliable confidence intervals for LM-based information retrieval evaluation. It's our main conclusion in this paper. We've proposed the methods that use prediction-powered inference and conformal risk control that only require a few ground truth labels. We can get tighter and better coverage than traditional bootstrapping. And also with CRC, we can get the first query level confidence intervals. I thank you very much for your attention. Yeah, thank you.